So, what we have here is a plane is inclined at an angle B to the horizontal. Uh, a plane is inclined at angle B to the horizontal. A particle is projected up the plane meaning that gravity is going to be acting against it for Sx and Sy, or Vx and Vy. With initial speed v at an angle alpha to the inclined plane. That's what we're used to. We're used to having an inclined plane, and we're used to having the thrown angle stacked on top of it. So it's our standard setup. A here, and then dot dot dot, and it comes back down again. Okay. Find the range of the particle on the inclined plane in terms of u, alpha, and beta. And then for part B, show that for a constant value of u, the range is a maximum when alpha equals 45 degrees minus beta over 2. Very nice question. Okay? So, when you see the word range, what does that automatically lend itself to? It's Sx at time of flight. Your range, when you're talking about the range, you're talking about this distance here. How far along the plane from start to finish. You're also talking about Sy being equal to 0 to find the time of flight. So in a way, we do not need Vx and we do not need Vy, do we? No, so you make that decision at the start if you want. So what we'll do is S equals ut plus a half at squared. And my whole job is finding Sx and Sy. That's what I need to find. So let's start by doing our velocity triangle. So our alpha is here. That's parallel to the plane. It's going at speed u. Break it up into its two components. What are its two components? U cos alpha and U sine alpha. Velocity triangle, tick. Gravity triangle, we haven't done it yet. So gravity triangle will be located here. I usually do it within the wedge. I do two parallel and perpendicular to the angle of the wedge. I call that angle beta. My gravity going directly down. This being my g cos b. This being my g sine b. Everybody alright with that? Okay. Next, I'm going to set up my formulas. So, my u value. What's my u value for Sx? Anybody? U value for the x direction, which is along the plane. So it's ut cos alpha. Is u cos alpha, but the t is there as well. Then take away my gravity. So minus a half. Anybody? Gt squared sine beta, yeah? The t squared and acceleration being g sine b. I like to put the sine b at the end. Now, I sort of have a lazy way of doing this. Once I do the first one, I don't even think about the second one, because the second one you just reverse the signs. Where you see cos, you put sine, and vice versa. So I just say that's ut sine alpha, and that's going to be minus gt squared cos beta. Just a quick time saver for you. Now, let's put Sx equal to 0. So that's our whole game plan is around this. Oh, sorry, Sy equals 0. Excuse me. Find the time of flight. Okay. So bring it over to your side. We get ut sine alpha equals a half gt squared cos beta. The t will cancel. Bring the 2 up. 2u sine alpha all over g cos b equals t. Time of flight right there, yeah? Now, let's put it into the range formula. So I need to bring down Sx now. Need to bring down all of Sx down here. And then bring all this back up here. Here we go. That equals 0 was there. Now, this little formula here is what I'm going to be working with. So that's it there. Important. Just so we keep an eye on it. Okay, let's begin. So, what we're going to have here is I'm going to just do t squared in the corner right beside it, just to save me the hassle. 4u squared sine squared alpha all over g squared cos squared beta. Is that alright? Just square it out before you even put it in. So ut, so it's going to be u cos alpha times whatever t is. T is 2u sine alpha by g cos beta minus a half g. What's t squared, guys? T squared? Yeah. Sine squared alpha over g squared cos squared beta. Now, gotta do a bit of cancelling here. Turn that into a 2. Actually, I'll rub it out at the same time. Probably save myself from a complete mess. 2. Cancel the g with the bottom with the g. Sorry, that's a g squared, so there's still a g there. Now it's a minus 1. Doesn't really matter anymore. Now, what do we have here? We have minus 2u squared sine squared alpha over g cos squared beta. Now, there's a what? Oh, there it was. There we go. Don't forget that sine beta. Be in trouble otherwise. Yeah. Yes. Okay. Now, what we have here is see the way they don't really have a common denominator at the moment. It would be g cos b, wouldn't it? So this would be u cos alpha. Sorry, 2u squared cos alpha sine alpha all over g cos b. They're not compatible denominator wise. So what I'm going to do is I'm going to multiply the bottom by cos beta and the top by cos beta, and that will get me my cos squared beta. Now they have a compatible denominator, so there's no worries there. I'm now going to factorize and see what they have in common. I'm going to factorize out 2u squared. I'm going to factorize out the denominator, and then I'm going to be left with what? Cos alpha sine alpha minus, anybody? Oh, wait. What else? What can I take out? Sine alpha, isn't it? Sorry, excuse me. Did that wrong. Go again. I took out the sine alpha, so I'm left with cos alpha cos beta. Yeah. And then after this, what am I left with? Sine alpha. Oh yeah, but I took it out though. See the sine alpha here? I took one of them out, and then leaving the other one in. Long story short, if I multiply this back out, I get back to my previous step. Okay. Now, see this cos, what can anybody tell me? Cos A, cos B minus sine A, sine B? Any guesses? Any guesses? Huh? I think it's cos A plus B if you look that up in your formula. Bracket cos, oh wait. Don't even need the second bracket there. Everybody alright with that? That is your range. Everybody cool with that? Now, sorry guys, just while we're here, this here is alpha. Still alpha and beta. Alpha is the thrown angle, and beta is the angle of the plane. Is that alright? Now, what I think I can change this to now, 2u sine alpha cos alpha. Okay. We could differentiate this is what we're going to try and do. Okay, it's going to be pretty difficult. So, can anybody suggest a logical place to split this up? Anybody tell me? I'm actually going. Okay. From the range, excuse me guys, the range is 2u squared sine alpha cos alpha plus beta over g cos squared beta. What you got to remember is that the 2u squared and the g cos squared beta, they're considered constants. Therefore, it's a constant out here. For a turning point, our derivative, which is dr d alpha, is equal to 0 because it's a turning point. Hence, we're looking for our maximum. Okay. Now, what I also want to show you is that the differentiable part is the alpha. So you might have remembered in the past where you'd be asked to differentiate sine 3x plus 2. Everybody agreed with that? And when you differentiate sine 3x plus 2, you change the sine to a cos. The angle is always the same. Then you differentiate the angle to get 3. So it'll be 3 cos 3x plus 2. In the same way, if that number 2 was a letter, like like the letter B, the fact it's a B still doesn't make it differentiable. The only thing that's differentiable is alpha, the thrown angle. B is not a variable because the plane is set with an angle of beta. The only thing that's a variable is alpha because you can change your thrown angle. That makes sense? Now, what we're going to do first is we're going to differentiate this, okay? So when you differentiate it, the constant goes straight in. So dr d alpha, okay, and this 2u squared g cos b stays exactly where it is. What we have here is a quotient rule, product rule, u and v. We're going to get u times the v dx plus v times the u dx. Now, differentiate sine alpha so that the u dx is cos alpha. Differentiate cos alpha plus beta. Please be reminded, beta is a constant, not a variable, and it's 1 alpha. So what you do is you change cos when you're differentiating your v dx. You change cos into minus sine, so minus sine alpha plus beta. You differentiate the angle, but because it's 1 alpha, it's just going to be a 1 on the outside. If that was 2 alpha, it'd be a 2 on the outside. If it was 3 alpha, it'd be a 3 on the outside. But it's 1 alpha. Okay? Next thing we're going to do is the quotient rule itself. Yes? So this here is cos squared b, okay? The constant is cos squared b. Okay? Now what we're going to get is u, which is sine alpha, and then the derivative, which is the v dx, which is minus sine alpha plus beta. The next thing we're going to get is plus v. V is cos alpha plus beta. And then behind that again will be du dx, which is cos alpha. Now, I have a tendency to put pluses before minuses. So I'm going to rearrange this full part in here. I'm going to rewrite it as cos alpha plus beta. Now this part here is a minus, so I'm going to put the minus second. Just tends to be what I always do. And then minus sine alpha plus beta. Now, I have a compound angle there. I recognize it from the formulas in the maths tables. Now, only problem is it's more difficult than usual. So I basically think of placeholder names, right? So I do cos x, cos y, minus sine x, sine y. This has nothing to do with the equation itself. It's just telling me that this equation down here, if x is represented by alpha, and y represents alpha plus beta, this formula here, therefore, is going to be cos x plus y. Okay? So this formula here is cos x plus y, but because it's cos x plus y, it's actually, technically speaking, it's cos alpha plus beta. This means that we have our constant dr d alpha equals 2u squared g over cos squared beta, and that is going to be multiplied by cos 2 alpha plus beta. Because it equals 0, this constant never mattered in the first place. Okay? And we know that cos 2 alpha plus beta equals 0. Cos 90 degrees equals 0. This must mean that 2 alpha plus beta equals 90 degrees. Bring over the beta. 2 alpha equals 90 minus beta. Alpha equals 45 minus beta all over 2.